This is the second video about solubility equilibrium, and there's two main topics in this video. The first one is going to be this right here, the common ion effect, so looking at how solubility will be affected if you mix two solutions that have an ion in common. And the second topic will be precipitation, so looking at if precipitation reaction will occur and how we can tell this, and specifically how we can determine when a precipitate will form. So if we start with common ion effect, so let's first look at an example of the solubility of solid silver chromate. So its KSP is right here on the screen. And if you were to mix it with a 0.1 molar aqueous solution of silver nitrate, so how will the fact that they have the silver ion in common, how will that affect silver chromate's solubility? So first of all, you need to be able to recognize what the common ion is going to be, and I already mentioned it. It'll be the silver ion. The initial concentration of silver ions is just going to be from the aqueous solution, so just 0.1 molar. The reason why we are not considering silver chromate is because it is a solid, so there are not going to be any ions. So we're just looking at the aqueous solution. And what is the initial? Remember, if you see this little 0 after the concentration brackets, that means initial. So what is the initial concentration of chromate? Well, that's going to be 0 because that chromate comes from the insoluble or the solid compound. What is the KSP expression? So as this reaction happens, as equilibrium is reached, some of the silver chromate is going to dissolve. And so we can write the dissociation reaction, and that is going to dissociate into 2 silver ions and then that 1 chromate ion. And so if we use this, we can write the KSP expression, and it would be the concentration of the silver ions squared, because its coefficient is 2, times the concentration of the chromate. All right, now we're going to look at a calculation that's going to be exactly like the calculation that we did in the last video using the icebox and using this particular equation. And we're going to see how the common ion effect works and how having an ion in common affects the solubility of that particular solid. So I already have it worked out for you, but I will explain the calculations and what I did. So I first wrote the equation. That's just a copy from the last slide, and we're looking at the dissociation reaction. Remember that solids are excluded from equilibrium, so we don't need that in our icebox at all. We have our initial concentrations, and the equilibrium is in fact going to shift to the right, and so you have to add an 2x to your silver. Remember, this 2 is because the coefficient is 2. And then we're going to take our values here at equilibrium and plug them into the KSP expression that we just wrote. So since the KSP is so small, remember that if you have KSP values that are times 10 to the -4th or smaller, we can make that assumption that the value of x is a lot smaller than this initial 0.1, and so that allows us to just get rid of this whole part, so to make the math a little bit easier. So we consider that x is negligible in comparison to the 0.1 that's initial concentration, and so we can just say that 0.1 plus 2x is essentially equal to 0.1. So then that gives us this new equilibrium expression that's a little bit easier with our math. And so we then do some algebra and solve for x. So the value of x is 9 times 10 to the -10th. And so we can then figure out your equilibrium concentrations of both silver, which again we're assuming to be about 0.1, and then the concentrations of chromium, the chromate ion. So if we go back and did the same calculation for the solubility of silver chromate, in pure water, it's going to be 1.3 times 10 to the negative fourth. If we look at the value of the solubility of a silver chromate in this common ion solution, the 0.1 silver nitrate solution, we get 9 times 10 to the negative fourth. So it's a much lower value. And so the conclusion that can then be drawn is that the solubility of a solid is lowered because of the common ion. So anytime you have a solid and you dissolve it in a solution that has an ion in common, the solubility is going to be much lower than it would if it was just in pure water. All right, here's another example, and I'm going to walk you through this calculation. It's going to be exactly the same as the last one, but I'm going to show you from start to finish rather than having it all worked out. So the question is, calculate the solubility of calcium phosphate, which has a KSP value of this, in a 0.2 molar solution of sodium phosphate. You will probably never be asked to state the common ion, but it's a good thing to note when you're looking at a question. So what's the ion that these two particular things have in common? And it would be phosphate. So we're going to first write the dissociation reaction for the compound that we're actually looking at, which happens to be calcium phosphate. And that's going to dissociate at equilibrium into 3 calcium ions and 2 phosphate ions. Set up our ice box. Remember, don't care about solids when it comes to equilibrium. Your initial concentration of the calcium ions is going to be 0 because the calcium is not our common ion, and so we're looking at this insoluble, relatively insoluble salt. The calculation or the concentration of the phosphate ions is going to come from this solution right here. So its concentration is going to be 0.2. And remember again, these two are coming from the sodium phosphate solution. So our equilibrium is going to shift to the right, and so we have plus 3x here and plus 2x there. Add this two together to get our equilibrium concentration. So we have 3x here. We have 0.2 plus 2x here. The KSP, remember you should always write the general expression. So calcium ion cubed times the phosphate ion, that should be 3, and that's going to be squared. Plug in the values that we have, so 1.3 times 10 to the negative 32, and you get 3x cubed times 0.2 plus 2x squared. Now we have a very small value of k, so we can make the assumption that 0.2 is much larger than 2x. And you should always write these assumptions just so the AP graders understand why, so they know that you understand why we got rid of the 2x. So we're assuming that this is much larger than 2x, so 1.3 times 10 to the negative 32 is equal to 3x third times 0.2 squared. And if you do that math, you end up getting that x is equal to 2.3 times 10 to the negative 11th, and that's going to be moles per liter. Now if we do the 5% check just to make sure, you don't really have to do the 5% check because this value for K is so small, the assumption is going to work. If you want to do the 5% check right now, you can, but it's really, for these types of problems, it's really not necessary. And so remember from the last video, the value of X, that is the answer to the question, that is the molar solubility. And so this right here is the molar solubility of the calcium phosphate. All right, the last concept that I'm going to cover in this video is looking at how pH affects solubility. So we just looked at how a common ion affects solubility. Now we're going to look at the pH. And so if we're looking at an anion, let's just call it X, and if the anion is an effective base, the salt that is made with that anion is going to have an increase in solubility in an acidic solution. And let's go back and look at some definitions. So an effective base is the anion from a weak acid. So if HX is a weak acid, then its anion would be an effective base. So here are some examples. Hydroxide, sulfur, carbonate, oxalate, and chromate are all effective bases, because if you were to form an acid with any one of these ions, it's going to be a weak acid. These are not the only effective bases, but these are just some really common examples that you may see. And so salts made with these particular anions are going to be more soluble in an acidic solution than they would be in pure water. Here's an opposite example. So this is looking at silver bromide. So silver bromide has the same solubility in water as an acid because Br is a very weak base, meaning it's not an effective base. It's a very weak base, because the acid that's formed with bromide is going to be a strong acid. So when that happens, no HBr molecules are going to be formed, because it's going to immediately dissociate as soon as that happens. And so if you were to add some hydrogen ions to a solution that contains bromide ions, it's really not going to affect the concentration of the bromine at all, and so therefore it has no effect on its solubility. So again, just to summarize this, if you have an effective base or an anion that comes from a weak acid, the solubility of the salt that's made with that anion is going to increase when you add it to an acidic solution, or you try to dissolve it in an acidic solution. If you have an anion that comes from a strong acid, so it's a weak base, then the solubility is not going to be affected at all in an acidic solution. It's just going to remain the same as it would in water, because in water it's going to be dissociated anyway. And so if you add more acid to it, it's just going to keep dissociating. So the solubility is really not going to change. Another example to silver bromide would be silver chloride, or maybe lead 2 chloride. All of those are going to have the same solubility in water as they do in an acidic solution, because they both have the chloride ion, and the chloride ion comes from hydrochloric acid, which is a strong acid, so it is a very weak base. So its solubility is not going to be any different in water. It's not going to be any different in an acid as it is in water. All right, and in the next video, I will continue with the notes looking at precipitation reactions and determining when a precipitation reaction will happen, when the precipitate will form, when it will not, that sort of thing.